Hearing problems can include several things. First, you can have an obstruction of the ear canal. It's something that physically blocks the auditory canal. And this will impede sound from reaching the eardrum. There should be a period right there. Impede. Because if you think about it, you know, it's your head, there's your ear, it's kind of a big thing. And then you have this canal that goes down to your eardrum. If I have something that is blocking this, then the sound waves as they come will just stop right there. So an obstruction of the ear canal can cause can keep sound from reaching the eardrum or the tympanic membrane. And you know, that can be earwax or water, dirt, whatever, swimmer's ear. When you get water in there. You can also have a perforated eardrum. Where the eardrum is actually damaged in some way, usually because of really loud sound or maybe from sticking things too deep into your ear that will actually impinge upon the eardrum. That's very difficult to fix. Middle ear infection. You can get fluid buildup behind the eardrum. Remember, that's the middle ear behind the eardrum. And a middle ear infection can cause fluid buildup behind the eardrum, so it can't vibrate properly. Most hearing loss in the cochlea is due to the loss of hair cells. Or other problems. This can be caused by disease, age, or loud noises. And then finally, brain injuries can also affect hearing. So we have several classes of things. We have classes that will actually keep sound from reaching the ear, that's like an obstruction, or things that keep the eardrum from operating properly, that would be a perforated eardrum or a middle ear infection. Or then you can have more central problems in the inner ear, like the cochlea can be damaged, the loss of hair cells, or a brain injury, which just affects the way that you interpret the electrical signals that come from the cochlea. Now, intensity of sound. Sound carries energy, like all waves. And we measure not the energy of sound waves, but instead we measure the intensity. And intensity is related to energy. In this way, the intensity is equal to the power divided by the area. So P is power. We've seen power before. Remember, it was energy per time. And then A is area. Not sure if you remember the unit for power, but it was the watt. And so the units of intensity are watts per square meter. So when I think about the meter, let's say that I have a source of sound right here, a speaker or whatever, and it emits sound. And it has a certain power output. That power is energy over time. If I stand really close to the source of that, if I stand really close right here, then the intensity is going to be pretty big. But over here, the intensity is going to be smaller because the energy is spread over a much larger area. In fact, I know that intensity is power over area, and the area of a sphere is 4 pi r squared. The area always goes as the square of the radius. So that means that if I go twice as far away, if I double my radius, my distance from the source, this is r, then that means I'm going to have, excuse me, not 4, but a quarter the intensity of what I had before. Okay, so intensity is power over area, and it's very important to understand that the further we get away from the source of sound, then the more that impacts the intensity, because it's a quadratic relationship, an inverse quadratic relationship. That is that I is proportional to 1 over r squared. So whatever I do to R, say I double R, I triple R, then that is even greatly impacted in I. So if I double R, I quarter my intensity. If I triple R, my intensity is 1/9 its original value. Regarding intensity, there are two important points. That's the threshold of hearing, which is 10 to the minus 12th watts per square meter, and the threshold of pain, which is 1 watt per square meter. And I show you these to illustrate that the human ear can cover more than 10 orders of magnitude of sound. And that's quite remarkable. We'll see that the eye is a similar thing, that it can detect such a wide range of light intensities. But the ear can cover over 12 order, over 10 orders of magnitude, 12 orders of magnitude, from 10 to the negative 12th all the way up to 10 to the 0th power, or 1. And that's remarkable. That is terribly remarkable. We have no instruments that can detect such a wide range of sound. Both of these, of course, are dependent upon the person, because every person is a little bit different, but those are sort of typical values, and also the frequency. So as we all saw in class, that if I have a 20,000 hertz frequency sound, no matter how loud it is, I'm not going to be able to hear it. Or if I have a 5 hertz sound, no matter how loud it is, I'm not going to hear it. Now the 5 hertz sound, and maybe even the 20,000 hertz, you'll be able to feel it in some sense in your body, but you won't be able to hear it because your ears are not sensitive to that frequency. So depending on the person and the frequency of sound to which that person is most sensitive. And remember, our frequency goes from 20,000 hertz or 20 hertz all the way up to 20,000 hertz for the typical healthy person, but that window gets smaller and smaller and smaller on both ends as you get older, or if you have hearing damage. If we assume the source is a point source, then the intensity, okay, I've already said this, but let's just reiterate it. If we assume the source is a point source, the intensity can be written as P over A. That's equal to P over 4 pi r squared, where r is the radius of the sphere. And so what happens is r increases, well, I will decrease as r increases. But just a little increase in r causes a big increase in I. And this is an inverse square law. The inverse square law is very common in the physical world. Inverse square law is that I is proportional to the inverse and the square of the radius. And it's so common in the world, the inverse square law, we'll see it again and again as we move on. Actually, we've already seen it already, like the universal law of gravitation. I think we saw that earlier. The inverse square law is so common in nature because of the spherical symmetry of our world, that so many things are of spherical symmetry. It forces the way that energy propagates. This only applies, this inverse square law, if the sound is emitted in all directions. And so that doesn't hold with megaphones, speakers, etc. in all directions, because we're assuming that our source is here, and then the sound goes out in concentric spherical, in a sphere as it propagates outward. And as we talked about before, the area of that sphere is equal to 4 pi r squared. And since intensity is power over area, that's where that 1 over r squared term comes from. All right, so sound intensity level. I want you to have sort of a working knowledge. We're going to show you the equations, but you're not actually going to use the equations. So I'll point out, let's just sort of see it, and then I'll point out to you what I want you to know about sound intensity level. First of all, if the intensity of a sound, say we have a sound, and say that it's 10 times the intensity of that of another sound, a person does not perceive it to be 10 times as loud. In fact, they only perceive it to be about twice as loud. And that's what allows a person to be able to detect such a wide range of volumes or intensities in sound. Because if we multiply it by a factor of 10, we don't really hear it as 10 times as loud. But because of this fact of human beings, the way that we perceive sound, we use a logarithmic scale. If you're unfamiliar with the logarithmic scale, you might want to Google it and just sort of get an idea of what it goes as. But normally when I have a scale, I do 1, 2, 3, 4. But in a logarithmic scale, I don't start at 0. Instead, I start at 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. And so this scale increases more and more as you go up. So I go from 10 to the 0 is equal to 1 to 10 to 100 to 1,000. So in a logarithmic scale, the scales increase more and more as you go along the axis, because you're increasing by factors of 10, not by adding 1. This scale measures the sound intensity level. So the sound intensity level, which is L, we can say is 10 times the logarithm of I over I naught. This is measured in decibels. Actually, so you've seen this before, I'm pretty sure. It's in dB. You've probably seen it with regards to sounds. Actually, the true SI unit for sound intensity level is not the decibel, but the bell. And I don't know if you remember back when we did metric prefixes, we mentioned in passing a metric prefix that we don't use that often, and that's the metric prefix deci, which is where we get this factor of 10 that comes in here. So if I was just measuring it in bells, which is the SI unit for a sound intensity level, I would not have that factor of 10. But we use, for whatever reason, decibels. Here, I naught, this is our intensity. This, I naught, is the threshold for hearing. And so we saw that before. That's equal to 10 to the minus 12 watts per square meter. Now, we can compare the intensity of two sounds in this way. The intensity of two sounds is equal to 10 to the delta L over 10. So the result of this is, don't worry about the equation so much on this, but the result of this is that if I have a change in 10 decibels, then that results in a sound that's 10 times as intense. That is, if I, say, go from 20 to 30 decibels, I have a change in 10 decibels, then that means that my sound is times 10. Not plus 10, but times 10. Let me show you some examples, because you are responsible for knowing sort of how this works in the logarithmic scale. So for example, 30 decibels, we've already seen this, is 10 times as intense as 20 decibels. 50 decibels is how many times as intense as 30 decibels? Well, 50 is plus 20 is 30 plus 20. So I've increased it by adding 20. And so every 10 that I add a factor of 10. So that means that this is 100 times as intense as 30 decibels. That would be 10 times 10. Because for every 10 decibels that I add, I increase this by a factor of 10. Let's do some others. So let's say that I'm going from 10 decibels to 50 decibels. How much more intense is that? Well, I've increased by 40 dB. to get to this 50 decibels. That means I've increased by 10 plus 10 plus 10 plus 10 in order to get to 50 dB. But for every increase in 10, I multiply by a factor of 10. So it's actually going to be 10 times 10 times 10, which is going to be 10 to the fourth, or 1 with a 4 zeros behind it. 10,000 times as intense. You will see problems like this on the test, so please make sure that you're capable of doing this. Say, for example, I went from, I don't know, 30 to 60 decibels. Well, I have to add 30 decibels to get up to this. That means I had to add 10, 10, and 10, but because I'm on a logarithmic scale, these increases, these adding of 10s are actually multiplying the intensity. So it's going to be 10 to the third, which is the same as 1,000 times as intense. All right, that's what I want you to know. One, just sort of the basics of the logarithmic scale, that it is a scale that increases by factors of 10. And so the logarithmic scale, which is very important in the scientific world, because we have things that increase on large scales like that, and so we use the logarithmic scale often. I want you to understand the basics of the logarithmic scale, and then I also want you to understand this, that when I add 10 decibels, that increases the intensity by a multiplicative factor of 10. The equations, not so worried about the equations. You're not really going to see the equations on the exam, but you are going to see questions like this. All right, let's look at some ways that we can protect our hearing. Earplugs block sounds from entering the ear canal. They block sound waves from entering the ear canal. You should always wear earplugs whenever you're around loud sounds. Like if you're using power tools, for example, you need some good earplugs, or even better, some ear muffs that go on your ear. If you go to a loud concert, good idea to wear some earplugs or get as far away from the speakers as possible. When you damage your hearing, it's mostly irreversible. Right? The earplugs are rated by the noise reduction rating. That's your NRR, and the NRR is in decibels. So for example, a rating of 20 decibels should decrease the intensity by what amount? They should decrease the intensity by a factor of 100, because 20 is 10 plus 10, so that would really be 10 times 10, or a factor of 100, and it's decreasing, so it's 1 over 100. A good pair of earplugs, you won't be able to hear anything. I take them when we go camping, and if I can get them inserted properly, which is deep down into the ear canal, they should fit almost completely into the ear canal, and then they expand. A good pair of earplugs, you won't be able to hear anything at all. You won't even be able to hear a cricket chirp or somebody shifting around inside the tent. Certainly you can't hear college students playing their music too loud. All right, another means of sound reduction involves the interference of waves. I don't know if this is in your book. I don't think it is, but I include it here because it's interesting. The interference of waves, noise canceling headphones, for example. Actually, first, let me tell you what interference is. If I have two waves, say a wave like that and a wave like that, these two waves are going to add up to equal nothing at all. And similarly, if I have two waves and I add these up, these two waves will have a bigger amplitude. So peaks and peaks line up, troughs and troughs line up, or peaks and troughs line up to give me nothing at all. That's the concept of interference. It occurs in all types of waves, mechanical waves, and longitudinal waves, these compressional waves like sound. Noise canceling headphones use this. They detect the ambient noise and they produce an out-of-phase sound wave. So if this wave is of a certain phase, this is out of phase. It's shifted over so that the peaks line up with the troughs. We'll see this a little bit later when we get into light, because we see that light waves also interfere with one another. Out of phase simply means that the peaks and the troughs line up, whereas over here, these two are in phase, where the peaks and the peaks line up. So if you're listening to your headphones, here you are, you have your headphones on. Your headphones, your noise-canceling headphones, actually have a microphone over here that detects any sounds that come in. And those sounds that it detects, say that the sounds might look like this, it's going to produce another sound that it will play into your ear that has a waveform that is out of phase with this one. So let's see if I can do this. It's going to produce a waveform that will look like that. So when you add these two together, they're going to cancel out with one another. Those are noise canceling headphones. They're quite interesting because they get rid of ambient noise by creating another noise, a noise that has a waveform that is out of phase with the sound, the ambient noise that you want to get rid of. All right, so noise, goodness, where am I? Some sounds are unwanted. These are called noise. White noise can be soothing if it's at the correct frequency. That's why people will often, I guess often maybe, when they'll have like a noise generator that helps to soothe them, maybe to help them sleep, or sometimes when people are testing or doing, like if you walk over to the dyslexia center, you'll see that they have a little fan outside of the testing center that will help to mask other sounds. All right, hearing aids. Some hearing aids only amplify the sound. At the same frequency, while others modulate the frequency. So some hearing aids will take a sound like this and just make it louder. Just make the amplitude bigger. But some hearing aids will take a sound like this, and they might not even make it louder, but they'll just change the frequency of it. Make it a higher or lower frequency that you can hear better. And that depends on the patient, depending on what type of hearing loss they have. Some might just need it to be amplified, and others might need the frequency changed. Cochlear implants are much different, but they're a similar hearing aid. The cochlear implants are actually attached to the cochlea, and they send an electrical signal to the brain via the auditory nerve. You might have seen somebody with a cochlear implant. Don't see them that often, but they're quite remarkable. Usually they have some small thing on the side of their head. They might even have like a hole behind their ear where the cochlear implant is connected to the auditory nerve. And it detects those vibrations on the eardrum and translates that into an electrical signal. Now, it might take a little while, but eventually the brain will figure out how to interpret that electrical signal. It'll be a little bit different than what the cochlea gives you, and translate it into the sounds. All right, ultrasound imaging. Ultrasound is a handheld device. And it emits a very high frequency sound waves. High frequency, like 1 to 20 megahertz. So we can hear, the highest frequency we can hear is 20,000 hertz. This is beginning at 1,000,000 hertz and going up to 20 million hertz. They're emitted, and then some of those waves are reflected back. The device detects the reflected waves and it calculates the penetration depth. So for example, there's your baby inside of a belly, and so you have this device that emits these high frequency waves, and then some of those waves are reflected back, and it measures the time of the speed at which it travels, and can actually create an image of that object, baby, or you can use it to look at other things inside of your body. Ultrasound imagers can measure real-time motion, including babies and blood flow and your bladder, your gallbladder, babies and blood flow in a person. Let's see, we'll just leave this off. The resolution is about the same as the wavelength. The resolution for ultrasound imagers. Remember the wavelength, that's that lambda, with the frequency about 3 million hertz and the speed of sound is about 1,500 meters per second. Then the wavelength is about V is equal to F lambda. So lambda is equal to V divided by F. 1,500 over 3 million is about 0.0005 meters. That is a 0.5 millimeters. A millimeter, is about a little bit, I don't know, a few sheets of paper is about a millimeter, and you're looking at a half of that. So that's pretty darn good resolution when you're looking at something like a baby, for example. It's not just for imaging, ultrasound. It can also be used to heat the tissue for restorative purposes. It can be used to ablate cancerous tissue, ablation of cancerous tissue. And breaking up kidney stones. You might have known somebody that's had their kidney stones broken up by sound, by ultrasound. All right, let me show you these questions. You stand 1 meter from a point source of sound and the intensity is I. If you move to 2 meters away, what's the new intensity? Remember, I is equal to the power over the area, and that's 4 pi r squared. So if I double the radius like I do here, I get a quarter of the intensity. Damage to the cochlea is usually the result of loss of hair cells. Intensity is defined as power over area. 50 decibels, well, it's 20 decibels different. That's 10 plus 10, so it's 10 times 10, or 100. What these is the lowest intensity that a person can hear. That's that 10 to the minus 12th. And then noise canceling headphones operate because of the interference of sound waves. Again, not sure if that's in your book, but I want you to understand about interference, what it is, and then how it's used in noise canceling headphones.